Hello, my name is Tom Watson. Welcome to JakartaOne and my talk about InstantOn startup for Jakarta MicroProfile Spring Boot using checkpoint and restore. So just a little bit about myself. Like I said, I'm Tom Watson. I work at IBM. I'm a senior software engineer here. I'm based out of Austin, Texas, and I have a focus on open source software for cloud native Java technologies. Most of my time right now is spent in the Open Liberty project, which is our open source project for implementing Jakarta EE as well as MicroProfile, among other things for our runtime. I've also been involved with quite a few other open source projects over the years, namely the Eclipse project, and I lead up the Equinox project there that provides the runtime for the Eclipse IDE, and I've been involved with the OSGI specification and various other open source projects, both at Eclipse as well as at the Apache Foundation. But for today's talk, let's focus in on some of the cloud challenges. As we've seen, our customers and our developers move over to deploying into the cloud, we've seen a number of challenges, and in particular, some challenges with the Java runtime and the Java frameworks. So as we see our customers move into this cloud native era, within our project, we focus on kind of these three different topics. The first there being developer delight. So for those that aren't familiar with Open Liberty, it's been around for about 10 years. So we really started on this Open Liberty journey before a lot of the big push to cloud native. But back then, we saw this need to help our developers become more productive as they're developing applications for, back then Java EE, but now Jakarta EE and MicroProfile. So we needed to provide a runtime that was, lightweight, fully functional, something that they could run on their local environment as they're developing their applications and testing against it. This is where Open Liberty was born. We wanted to provide something that we call a fit-for-purpose runtime. So for your application, if you only need like the servlet engine or CDI or Jakarta REST, you can enable just these features, and then it will only load those up, and it'll run much more efficiently, less memory, and all that kind of stuff. And so these kind of features that we added into Open Liberty really also play well as we transition into the cloud native era, and really make it an ideal runtime to consider using when you're deploying your applications to the cloud. Next comes cloud agility. As industries and companies are moving into the cloud, part of the motivation is they want to be able to focus on their own business innovations. Try to invest less in the IT infrastructure and their own maintain their own server instances and so on, so that they can invest more heavily into their own domains, their own business innovations, and then be able to accelerate their application delivery into the cloud. But once they start doing this transition into the cloud, this third thing comes up where they need to pay attention to operational efficiency. Now that they don't own those resources, anytime they're using anything into the cloud that's serving their application, it starts costing them money. So we need to help our developers and our businesses to reduce those costs as much as possible, so that then again they can keep investing into their own business innovations and not have to have these huge high cloud costs as they're moving into the cloud. So all these kind of demands have placed additional challenges onto our Java application frameworks, as well as the underlying JVM technologies. So this is where cloud economics comes into play. I mentioned having to have operational efficiency, and some of this is probably most people are aware as you're deploying into the cloud. It's comes across as this pay-as-you-go pricing model. So depending on how much your applications are using with respect to CPU, memory usage, and so on, These things all cost you memory as your application is running. The other thing that becomes important is you want to be able to elastically scale your applications. So as additional traffic is coming in and your applications are getting more and more demand by the users, you want to be able to scale out and fire up new instances of your applications so they can handle the increased load that's coming in. But each of those additional instances of your applications or the additional memory and CPU all will cost you money over time, and you don't want to leave the maximum number of instances running that you'll need for a particular point in time. As your application gets used less, perhaps during certain times of the day, you want to be able to scale those application instances down. And hopefully, if you have a certain period of times with no activity, you'd like to go down to 0 instances. So you're not paying for any of those costs of that application running in the cloud. And you need to pay attention to the memory that it's using as the application is running. And then finally, whenever you do see that increase in demand, you need to be able to quickly start up your application instances. So this is where the fast startup comes into play. If you have applications that take, say, like 10 seconds to start up, your users are going to start really seeing high latency if they happen to come online whenever your applications are trying to start up. So we really want to reduce that latency by having really rapid startup times for your applications. So we really need to be able to do more with less with respect to CPU and memory and so on. So let's go into a little bit of detail on why Java startup is slow. As you know, Java is an interpreted language. If we're running the interpreted bytecodes, that runs quite a bit significantly slower than, say, a native executable. So this is where the JIT compiler comes into play. It can start compiling that code on the fly as it's running. It can find code that gets run much more often and highly optimize that over time. And then eventually you get to this point where you have what we call peak throughput, where we've done all the optimizations that we need in order to get the application running and serving as fast as possible. And that time that it takes to get there is that horizontal arrow there at the top. That time and CPU will cost you money before you can get to your peak performance. And the JIT compiler, as it's doing these optimizations, takes up additional memory above and beyond what your application is using. But then once it's all done, you can reclaim that through garbage collection. But that additional delta of memory, you need to make sure all your application instances have that available to them while we're ramping up. So that's additional cost there as well as far as memory usage goes. So the goal, or one thing we would like to do, is try to get the startup time to get to that maximum performance as quickly as possible. Is there a way that we can avoid this additional ramp up time of just starting up the application and doing all of this work in order to get to that peak performance? So over the years, there's been AOT, which stands for ahead of time compilation. So this is basically statically compiling your Java application into a native executable. So for example, the Graal VM has its native compiler. And what it does is it takes your application, it uses a closed world assumption where it can figure out all the code paths of your application and the runtimes that you're using. And it can compile those all into a small package that ends up being a native executable for whatever platform you're deploying to. And this has obvious advantages. Since you're doing all that compilation into native code, there's no longer a need for this JIT, so you don't have that JIT overhead with the CPU or the memory. And then the fact that it's just native code means that it immediately is just going to start up extremely fast. So we can see, moderately sized applications start up in well under 100 milliseconds. So they can really start achieving that scale to 0 and then ramp back up very, very quickly. But it does have a number of compromises. Whenever you start compiling into the native executable, there are once you're running, it's not going to be that full Java environment you become used to. Some things are a little bit more difficult. For example, reflection. There are tools and runtimes to make that easier, like Quarkus, for example. But there are certain things that don't work quite the same whenever you're running as a native executable. So it comes where you kind of have to retest how it works natively compared to when you're running on the full JVM. And you don't necessarily have all the tools that you do, like the Java debugger and other things that we've come used to with the full Java stack. The other things is now without the JIT compiler actually can make additional optimizations above what a static compiler can do for high traffic code. And it'll actually, we can see peak throughput become better over time when we're running on the traditional JVM. The other thing is the garbage collector for the standard Java stack has been developed over decades now and is very, very efficient at what it does. So it can help reduce latency as the garbage collector has to do its work. The native garbage collector it is improving it over time, but there's still some differences that make the traditional JVM one perform very, very well. So with all this in mind, we have taken we want to take an alternative approach where we want to get basically to here, where we can retain the Java, um, all of its features as far as what the JIT compiler can do, the garbage collector, and all the full benefits of the JVM. But we want to try and approach that kind of startup speed of native compilation and try to reduce the amount of memory that's needed for, say, like the JIT compiler as we're ramping up your application in the runtime. But can we do this in such a way that we retain all of the Java features? So within Open Liberty and as well as the Semaru runtimes, which is our Java runtimes that's based upon Eclipse OpenJ9, we're taking a look at using something called checkpoint and restore in order to achieve this kind of rapid startup. So we call this effort Liberty InstantOn. So it's a solution that, like I said, is based upon the Semaru runtimes and the Semaru InstantOn capabilities that are provided by the OpenJ9 runtime. And it provides this holistic solution for rapid startup without compromising the full functionality of the JVM. And it uses this technology, Checkpoint Restore, which the implementation is provided by a project called CRIU. And CRIU is a Linux project hosted out at GitHub, and this is a Linux-only solution. So we really focus in on containerized applications that are creating things like Docker containers that are running on a Linux host. And at, and with this technology, essentially what you can do is you can bring up your application process and then use CRIU to do a checkpoint. And what that does is it takes the full state of the process, including all of its threads, the Java heap, everything that's in memory, all the resources it's using, and it gets a snapshot of that state that it can persist into onto disk. And then CRIU can be used later, perhaps even on another machine, in order to restore that application process. And from the process perspective, it's just continuing on right from the point it was. It has all of its objects, all of its state that it was stored during the checkpoint, and then it can continue on and come fully up as a running process. So for Liberty, the question becomes, where do we checkpoint? And how can we do that in a safe way such that we can restore that instance multiple times into unique instances of the application instance? And then, like I mentioned, we really focus on the container support. So we view this as kind of a technology that we can use during our container image build you can do this checkpoint of your application process. And then whenever that container image is started, we can very quickly bring that application container up and get it ready to service requests. So like I mentioned, the question becomes where to checkpoint. So for Liberty InstantOn, we currently offer two options. One is called before app start, and the other is after app start. So with Liberty, during its startup process, it has something called a kernel, which is just the very base of Liberty that has no other features. Doesn't include even the servlet engine or any CDI or any other implementations of like Jakarta or MicroProfile. And it starts processing the configuration, figures out what features need to be enabled. It loads all those up and then starts processing the application. So looking at its metadata, its configuration, any annotations, starts getting the container up and ready to start running the application. At this point, we have the before app start, which will do a checkpoint before we actually run any application code. So any code that needs to be run during the application start, such as early start servlets or CDI beans that are paying attention to application scope events, EJB early start beans, and so on. These kind of things are not done yet whenever we're using before app start. The after app start then is done at a later point, and this is, of course, can happen after we've run some of that application code. And the reason you would choose one before the other, of course, ideally you'd always want to choose after app start because that'll give you the quickest startup time. Because after we restore, we really literally just have to open up the Liberty ports, the ports that were taking incoming requests in order to service your application. But some applications may be doing things during that early start that you can't necessarily do during a container image build, for example, like accessing a remote database with some credentials. You wouldn't want to do that while you're doing your application container image build. So that's where we leave this option to do before app start. So we can reduce all the overhead of bringing up Liberty itself, but we just get to that point where we're going to start your application. So let me go ahead and get into a demo of this. So for this demo, I'm just using a sample getting started. This is out on GitHub. So it's just a sample getting started. It's a very simple REST application that uses various parts of MicroProfile like health, metrics, and config. I won't go into a whole lot on the application other than I'll show it running, but it just has a simple endpoint for getting the Java properties. So it's pretty simple. But the thing I do want to focus in is how do you containerize such an application? So this particular application is a Maven project. I've already built it, so it has the war in the target folder. Then I have some Docker files. So we'll just do the normal Docker file here. So whenever we're containerizing applications with Open Liberty, we recommend we use one of our production ready images. So here, this is our Open Liberty kernel using Java 17, and it is of course using the OpenJ9 Semaru runtime. And there's really just three things you have to add in. First is the configuration. This is what tells Liberty which features to enable for your application, like REST and so on. And then we have this features script that you run after you've copied in that config. And the features script will process that configuration, determine what additional features of Liberty need to be installed, servlet, REST, whatever you have. So it only will layer in that part of the runtime. So you don't have to have the full runtime included into your application image if you don't need it. And then it copies in some additional resources and the actual application. And this final step is the configure script. So this is just a script that ends up optimizing your runtime. Since we're based upon the Semaru runtime, it establishes things like the shared classes cache, and basically gets all of our other caches tailored to your application, established so that whenever you run this application, it can bring it up as quickly as possible. So this isn't actually using any InstantOn yet. This is just standard containerizing your application. So if I go ahead and build this, so I've already built, I already did the feature script because that's just coming from the cache, but I did rebuild the application. So it had to copy in the new application var, and now it's running that configure script. So this is the thing that's establishing all the caches. It basically brings the application up and runs it, and the J9 is basically kind of profiling the application, getting all the uh, classes processed and into their shared classes cache so that on a subsequent restarts that can start up that much quicker. Typically, this takes just around 10 or 15 seconds. But once this is done, I'll show how do you layer on top of this Liberty InstantOn process. So hopefully this will finish in just a few seconds. My server may be taking a little longer than usual. There it goes. And now it's committing the application. And so now we'll go ahead and look at the Docker file for doing checkpoint and using Liberty InstantOn. So it's identical up to this point, and now this final instruction is basically telling the runtime that it wants to do a checkpoint, and I'm using the after app start option. So you can use either after app start or before app start here. And so this was just going to do that layer on top of what I've already built. So if I build this guy, so you'll notice it's just using the cache that it did before for when it's running that configure script. So I don't have to do that part again, but now I'm doing the after app start checkpoint. So here we'll see Liberty starting up, and it's processing the configuration, processing the application, and then it actually started that application. And at that point, it's doing the after app start checkpoint. And here's where Liberty will prepare the runtime itself, and then it hooks into the Semaru runtime and asks the JVM to do the checkpoint. And at that point, the JVM does all the preparation it needs, gets everything into a good state, and then asks CRIU to go ahead and checkpoint the process. At that point, we exit the build, and we've committed this new application, getting started InstantOn. So first, I guess I should run the original one, the original application image, just to show you it running without InstantOn. So typically this takes just around anywhere from 7 to 10 seconds to come up, depending on my server. So this came up just right around 9 seconds. So this is a pretty simple application. Like I mentioned, it just contains the endpoint for system properties, and then some widgets down here showing the health and config and metrics and so on. So that's the application up and running without InstantOn. So once I quit, you definitely see it. It's not here anymore. So now I'm going to run it with InstantOn. So you'll see it came up much quicker. It reports it came up in just under 400 milliseconds. So definitely more than 10 times fast, perhaps closer to 20 times faster to bring this up and running. And now we have the application up and running just like before with the properties endpoints and the various stuff from MicroProfile. So as you can see, I didn't have to do any changes to the actual application. I just had to layer on top of the existing application image without InstantOn this additional layer that contains the state of that application process. And it put it into a state that was safe so that I can restore this over and over into unique instances of that application as we're trying to scale out, from a scale to zero type scenario. One other thing I wanted to show is is how we would go about debugging. So so that so with J9 we can add additional Java options on restore. So for example, if you need to do some xtrace stuff as you're restoring, you can set an environment variable that tells it what do we want to xtrace. So this particular example, I'm just going to say print out something for every time we call thread.sleep. So I'm not changing the application image. I'm just passing in this additional environment variable to that thing. Now, of course, whenever we do that, you'll JNI is going to report that it no longer is going to be using the compiled code. It has to do things interpretively. So of course, it's going to start up much slower. But we'll see where it's will print out the stack traces. So we can start getting debug information even from this checkpointed process, because and we have the ability with OpenJ9 to change some of the JVM options even on the fly for this existing process that we're restoring. So we can still, with this approach, be able to retain that full Java debug facilities and everything on that restore side, so that when we're up and running, we can service that application if needed. Okay, so that's the end of the first demo. Then the next thing I would like to go into is a project called CRAC. So if you're familiar with Checkpoint and Restore, if you've heard of Checkpoint and Restore, you probably have also heard of an open JDK project called JDK.crac. So this is another approach at using Checkpoint and Restore to help with rapid startup of Java applications. And they have this uh, I call it like a sister project called org.crac, which provides an API layer abstraction above a JDK.crac solution. And the intention of it is basically to provide a smooth transition into this kind of CRAC solution. And the basic idea behind CRAC is, now that we have this ability to checkpoint the JVM, that's all great, but we have certain cases where the application needs to participate in the checkpoint and restore process. So that's what the CRAC API is providing. And the basics behind the API is they have this interface called resource. Hold on. Great. My presentation just went out on me. Hold on. Sorry about that. I've never seen that happen. Here, it's coming up, so let me just get it back over here. All right. All right, here we're back. So, like I was mentioning, you implement what is called a resource, which anything from your application that needs to participate in checkpoint and restore, perhaps it needs to get some state into appropriate state to do that checkpoint, and then on the restore, it can recover from that and get it back into a state that's appropriate to on the running side when we restore the application. So anything that needs to do this will implement this resource interface and then register it with something called a context. And you can get what is called the global context from this core API, which has this static method called get global context. And so now applications can participate in this checkpoint and restore process, and you can compile against that runtime. Even when you don't have a crack enabled JVM, it'll just provide this abstraction. It'll be a no op. But then when you're on a crack enabled JVM, it'll do the right things whenever you're going to checkpoint your process, and then on the restore side. So why this becomes important is you may have heard recently the Spring project, the Spring 6.1, which was just released within the past month, is adding integration to checkpoint and restore. And they're doing that by using the org.crac library. So your Spring application, you can include this org.crac library within your application. And then once you're on a crack enabled JVM, it'll start participating in the checkpoint restore. And where the Spring framework participates in it is within what they call their Spring lifecycle contract. So any kind of lifecycle beans, like for example, the one that takes care of the embedded servlet engine like Tomcat or Jetty, that implements a lifecycle bean that will stop the runtime, stop it from listening to ports, and then on the restore side, it'll bring it back up and get it configured for however you want it on the restore side. And so Open Liberty, we offer an implementation of org.crac as well that can sit on top of our Liberty InstantOn solution. And that way we can enable Spring Boot applications that are running on Liberty to be able to participate in our checkpoint and restore process. Right now, this is currently in beta. We have it available in the 23.0010, which was released right around in October. And it offers up this implementation so that starting with Spring Boot 3.2, which again was just released, you can start trying to play around with this kind of checkpoint restore functionality with your own applications. So that was my next demo I was going to show, is something with using a Spring Boot application. So here, Open Liberty, we offer a runtime that can run, of course, Spring applications in your traditional WARs, but we also support Spring Boot applications that are just packaged as a Spring Boot application jar. And so this particular guide here that we have on Open Liberty IO is basically going through packaging up a Spring Boot application using the Liberty runtime. So I'm not going to go into all the details of that. If you want to look at the guide, that'll show you all how you do that. But I do want to show, so this is the Docker file after we've staged in the Spring Boot application. But the important part is, again, we have the configure script, and then we run this checkpoint. And here I'm doing after app start. So if those are familiar with Spring Boot applications, they have to run quite a bit of code before the application is started. So after app start is ideal for a Spring Boot application because you want to try and avoid all of that ramp up time to get that application started. So I'm going to go ahead and build this guy similar. Actually, let me build the original one first. So, okay. I thought I had already built this. So this is going to take more time than I'm going to want to take while it's running this configure script. So I'm going to, somebody asked a question, what would make sense? Would it make sense to standardize CRAC? Would it make sense to standardize CRAC APIs in Jakarta EE? So CRAC APIs, I'm not completely sure on. It's something to consider. I think something we can do though in Jakarta EE is just consider what specifications may be able to do in just a checkpoint and restart and restore scenario. And then kind of leave it up to the runtimes how they would plug into a checkpoint restore. So for example, like MicroProfile config, how do applications react to configuration changes that may happen whenever you're doing a restore? Because you may have some credentials or some other things you want to get fed in through that config, and you want to be able to react to that kind of changes on the restore side. So how can we enhance maybe npconfig, or do we just need to say rely on the CRAC APIs so that on restore using something like MicroProfile dynamic config, maybe perhaps you reread the config on restore and react to it? Or is there something that npconfig can do that it can recognize that, hey, some config has changed? Is there some additional way we can notify the application to react to that kind of configuration change? So those kind of things we can start considering. Maybe CDI needs some kind of ability to kind of do something like what the Spring framework did with its lifecycle beans. I realize there's not really equivalent to a lifecycle bean in CDI, but maybe there needs to be some kind of mechanism where a bean can say, during a checkpoint restore, maybe you do something to akin of stopping me and then starting me on restore. So these kind of things, I think it'd be interesting to start considering what we can do in the Jakarta space, as well as the MicroProfile space with respect to checkpoint and restore. All right, so this finished while I was answering that question. That was just building the original Spring Boot application. So let me go ahead and run this. So this is going to, of course, bring up Liberty, and then we'll notice the Spring application coming up. It's using the very latest Spring 3.2, which has the checkpoint restore, and then the application here is really, really simple. It's just a hello application, and then it prints out all the beans that are in it. It's not terribly interesting, but it's just greetings from Spring Boot. So it has this simple endpoint. But as you notice, it came up in right around 8.5 seconds. So it's somewhat equivalent to that MicroProfile one that we saw come up in right around 8 to 9 seconds. So let's go ahead and do the checkpoint. So now I just using the cache just like I did on the MicroProfile application. But here I'm again just layering on top of it the checkpoint after application start. And so we'll notice the Spring application is doing its thing. But then once we get to the point where the application is started, Liberty is doing its thing, getting the runtime ready, and then its CRAC implementation calls out to any resources that the Spring framework has registered. So here it's registered that default lifecycle processor. So this is the thing that will manage that and will stop all the lifecycle beans as we're shutting it down to get it ready to do the checkpoint. And then at that point, we did the checkpoint and we have everything saved off into that application image. So now I'm going to go ahead and run this, and we'll notice it comes up rather quickly. Here is just under 500 milliseconds. So the important thing to notice is that I enabled the debug for that default lifecycle processor. So this is the thing where it's starting those beans up again, getting everything up and running, and now we're ready to serve. So it's back up and running with that simple endpoint. Okay, so with that, that's the end of my demos, and also that's the end of my talk. So it looks like I have about 5 minutes left if there's any additional questions. But other than that, thanks for attending my talk. My contact information is down there, as well as my Twitter handle. So feel free to reach out with any questions or otherwise with respect to Liberty InstantOn. So it looks like no additional questions. All right, thank you.